From this we will see how to design the differential amplifier or a subtractor circuit using the op-amp. Now we already know that this op-amp is differential amplifier, which amplifies the difference between the inverting and the non-inverting terminal. But whenever this op-amp is used in the open loop configuration, then the gain of this op-amp is quite high, and because of that your output will always be get saturated. And to avoid that, we always need to use this op-amp in a feedback circuit. So then we had seen this inverting and the non-inverting op-amp configuration, where we have applied the input either to the non-inverting or the inverting input terminal. So now let us see how by combining the inverting and the non-inverting op-amp configuration we can design the differential amplifier. So by using this configuration we can use this op-amp as a differential amplifier in a true sense, because here we can control the gain of the op-amp by controlling the value of this resistor R2 and R1. So let us see how this configuration will act as a differential amplifier. So now if you closely look this configuration, it is the combination of inverting and the non-inverting configuration. So if you consider this voltage source V1 alone and consider this voltage source V2 as 0, then it will be the inverting configuration. Similarly, if you consider only this voltage source V2 and if you consider this voltage source V1 as 0, then it will be the non-inverting configuration. So this configuration is the combination of inverting and the non-inverting configuration. So to get the final output, we need to use the superposition theorem. So what we will do, we will consider only one voltage source at a time and we will consider the remaining voltage source as a 0. So first we will consider this voltage source V2 as 0 and we will assume that this voltage source V1 is acting alone. So let's 0 and we will assume that this voltage source V1 is acting alone. So let us say in this configuration the output voltage is VO1. So this output voltage VO1 can be given as minus R2 divided by R1 times this voltage V1, as it is the inverting configuration, right? Similarly, let us say if voltage V1 is 0 and let us say this voltage V2 is acting alone, then in that case our output voltage, let's say VO2 will be equal to 1 plus R2 divided by R1 times this voltage source V2. So now if we consider this voltage source V1 and V2 acting simultaneously, then our output voltage Vout will be equal to VO1 plus VO2, that is equal to minus R2 divided by R1 times this voltage V1 plus 1 plus R2 divided by R1 times this voltage source V2. So now if you observe here, the gain that is applied to both the input is different, and suppose if you want this output voltage Vout as K times the difference between the two voltages, let's say that is equal to V2 minus V1, then we need to ensure that the gain that is applied to both the input is equal. So suppose in this case, if the gain that is applied to both the input is, let's say that is equal to R2 divided by R1, then in a true sense we can use this configuration as a differential amplifier, where the output will be the difference between the two input voltages multiplied by the sum gain factor K. So now let us see how we can achieve this equal gain. So here in this second term, instead of this 1 plus R2 divided by R1, we required the term that is equal to R2 divided by R1. So somehow we need to arrange this term in such a way that we can get this term R2 divided by R1. So now we can write this term 1 plus R2 divided by R1 as R1 plus R2 divided by R1, and if we want this term R2 divided by R1, then we need to multiply this term by the factor of R2 divided by R1 plus R2. So here to get this term, what we can do, instead of applying this voltage source V2 directly, we can apply this voltage source V2 by using the voltage divider. So let us see how we can achieve this term R2 divided by R1. So here what we have done now, we have applied this voltage source V2 using this voltage divider circuit. So now if you see at this point, then at this point let us say the voltage is V plus. So this voltage V plus will be equal to R2 divided by R1 plus R2 times this voltage V2, right? So our voltage V plus will be equal to this term. Now we know that the output voltage V out because of this voltage source V2 will be equal to 1 plus R2 divided by R1 times this voltage V plus. So now if we put this value of V plus, then we will get 1 plus R2 divided by R1 times R2 divided by R1 plus R2 times this voltage V2. So if we simplify it, then we will get the term R2 divided by R1 times this voltage V2. So now if you see, if we consider this voltage source V1 and V2 simultaneously, then our output V out will be equal to minus R2 divided by R1 times this voltage V1 plus R2 divided by R1 times this voltage source V2, or we can say that our output voltage will be equal to R2 divided by R1 times the difference between the voltage source V2 and V1. So now if you see this configuration, here the output voltage is the difference between the two input voltage multiplied with the factor of R2 divided by R1. So in this way, using this configuration, in a true sense, we can use this op amp as a differential amplifier. So now let us see where this differential amplifier can be used. So apart from performing the mathematical operations, this along with the sensors. So let us say here we have a RTD and it is connected, and the output of the two arms of this balance bridge is connected as an input to the two ends of the differential amplifier. So here initially this bridge is balanced, but as the temperature changes, the value of this resistance R will change, and because of that the voltage that appears at the two input will also change. So when the bridge is balanced, then the input at the both ends of this differential amplifier will be equal, that is V1 equal to V2. But as the temperature changes, the value of this resistance R will change, and because of that the voltage that appears at this end will also change, and we can amplify the difference between the V1 and V2, and we can use this output to control the another circuitry. So let us say if we want to control the temperature of some room, then we can use this sensor along with this differential amplifier. So by triggering the another circuitry based on this output voltage, we can control the temperature of the room. So this is how this differential amplifier can be used along with the sensors. Now here the problem with this differential amplifier is that the input impedance of this differential amplifier is very low, and it depends upon the value of this R1 and the R2. So if you see in this configuration, the input impedance that is seen through this end will be equal to R1, while at this end if you see, the input impedance is equal to R1 plus R2. Or in general term, let's say if we are applying the input voltage between the two ends, then in this case the input impedance Zin will be equal to 2 times R1. So as you can see here, the input impedance of this differential amplifier is very low, and because of that it is quite possible that your source might get loaded. So one way we can avoid this by using the buffers before the input voltages. So as you can see here, before applying this voltage V1, suppose if we use the buffer, then the input impedance of this buffer is very high, and in this way we can avoid the loading of this source voltages. But in most of the practical cases where you are which is coming from the sensors, in such cases instead of this differential amplifier, the instrumentation amplifier is used, and we will talk more about this instrumentation amplifier in a separate video. So this instrumentation amplifier is a very high gain differential amplifier, and the main advantage of this instrumentation amplifier is that it is having a very high input impedance. So that is particularly useful when we are dealing with the sensors. But in our general applications, we can use this differential amplifier along with this buffers. So that is being said, now let us see some examples based on this differential amplifier. So here we have one differential amplifier, and we need to find the output voltage of this differential amplifier, and here assume that the biasing voltages which is being applied to this op amp is plus 15 and minus 15 volt. So here to find the output voltage, what we will do, we will consider one voltage source at a time. So first let us assume that this 2 volt voltage source is acting alone. So if we consider this 2 volt voltage source acting alone, then in that case let us say output voltage is VO1, and that will be equal to minus 5 divided by 1 times this 2 volt, and that will come out as a minus 10 volt. Similarly, if we assume that this 3 volt voltage source is acting alone and this 2 volt voltage source is equal to 0, then in that case our output voltage, let's say VO2, will be equal to 1 plus 5 divided by 1 times this voltage V plus, and here this voltage V plus is equal to 8 divided by 8 plus 1 times this input voltage, that is equal to 3 volt. So our output voltage VO2 will be equal to 16 volt. So now if we combine these two input voltages and assume that these two input voltages are acting simultaneously, then in that case our output voltage Vout will be equal to VO1 plus VO2. So our output voltage will be equal to 16 minus 10, that is equal to 6 volt. So this is very simple and the basic example based on this differential amplifier. Now here you also need to consider the biasing voltage that is being applied to the differential amplifier. So let us take one more example and we will see how this biasing voltage can affect your output. So if you see this example, this is very similar to the previous example, but here in this case let us assume that our bias voltage is plus 12 volt and minus 12 volt and we want to find the output voltage. So here once again what we will do, we will assume only one voltage source is acting at a time and we will find the output voltage, and then we will combine the individual responses. So let us say output voltage VO1 is the output voltage when this 2 volt voltage source is acting alone. So our output voltage will be equal to minus 5 divided by 1 times this 2 volt voltage source. So that will come out again as a minus 10 volt. And now let us assume this 5 volt voltage source is acting alone. So in that case our output voltage VO2 will be equal to 1 plus this 5 divided by 1 times this voltage V plus. That will be equal to 6 times V plus. Now this voltage V plus will be equal to voltage divider that is applied at this point. So it will be equal to 4 divided by 4 plus 1 times this 5 volt input voltage, and it will come out as a 24 volt. So our output voltage VO2 will be equal to 24 volt. So now in this case if you see, our total output voltage Vout will be equal to VO1 plus VO2, and if you see it will come out as a 24 minus 10, that is equal to 14 volt. But in this example we have applied the plus minus 12 volt. So our output voltage cannot go beyond this plus minus 12 volt, right? So our output voltage will be get saturated at the 12 volt. So apart from the input voltages, you also need to consider the biasing voltages which is being applied to this op-amp. So that is being said, now let us see the third example, and this example is for your exercise. So here instead of single input voltages, we have applied the multiple input voltages at the inverting and the non-inverting terminal, and we need to find the output voltage of this configuration. And here once again assume that the biasing voltages for this circuit is plus 15 and minus 15 volt. So try to solve this example by yourself and do let me know your answer in the comment section below. See how to use op-amp as a integrator. Now in the earlier videos of op-amp, we have seen that how to use op-amp as a summing amplifier and differential amplifier, and in these configurations so far we have used resistors with this op-amp. So now suppose if we use reactive element like inductor or capacitor along with this op-amp, then we can use this op-amp as a integrator or differentiator. So in this video we will see how to use this op-amp as an integrator by using the resistors and capacitors along with this op-amp. So first of all, just look at this inverting op-amp configuration, and in this configuration the feedback resistor RF is connected between the output terminal and the inverting input terminal. So now suppose if we replace this feedback resistor by capacitor, then the same circuit can be used as an integrator. So let us understand how this circuit will act as an integrator. So in this circuit, let us assume that the current that is entering into this resistor R is, let's say, IN, and the current that is going out of this node is, let's say, current IC, that is the current which is flowing through this capacitor C. And as this capacitor is connected in the feedback, so let us say this capacitor as CF. So now here, because of the feedback, this node will act as a virtual ground. So at this node the potential will be equal to 0. So let us apply the KCL at this node. So if we apply the KCL, then we can write it as a I in, that is equal to the IC, which is the current that is flowing through this capacitor CF. Now this current I in will be equal to V in minus 0 divided by this resistor R, and that will be equal to this current IC. Now if you know about the capacitor current, then the capacitor current IC can be given by the expression C times dVc by dt, where Vc is the voltage across this capacitor. If you don't know about it, then let us quickly go through it. So the charge across the capacitor can be given by the expression C times the voltage across the capacitor. So if we take the derivative of this expression, then we will get rate of change of charge, that is equal to the current, will be equal to C times dVc by dt. And here we are assuming that the capacitance is not changing with the time. So in this way we got this expression. So now let us use this expression and put this value in this expression. So if you put this value, then we will get V in divided by R, that is equal to CF times dVc by dt, where Vc is the voltage across this capacitor. So we can write this expression as CF times d by dt into 0 minus V out, which will come out as V in divided by R, that is equal to minus CF times d by dt into output voltage. So if we rearrange this expression, then we can write it as a dV out by dt, that is equal to minus 1 divided by RCF into input voltage V in. And if we take the integration at both sides, then we will get the output voltage as V out, that is equal to minus 1 divided by RCF times integration of input voltage. And here we are assuming that we have a no output voltage at this terminal before we have started the integration. Suppose we have an initial voltage at this terminal before the integration, then we can have a one more term that is equal to V out 0 plus, that is the initial output voltage before we have started the integration. So this is the expression of the output voltage in terms of the input voltage. So as you can see here, the output voltage is the integration of the input voltage, and here this term RCF represents the integration time of this integrator. So using this circuit we can integrate any input signal. So suppose if you apply a 1 volt of DC signal at the input, then at the output you will get this signal. So as you can see, initially the output voltage will increase in a negative direction, and at certain point the output voltage will get saturated, because the output voltage cannot go beyond the saturation voltage, right? Now here the rate at which this output voltage reaches the saturation point depends upon the value of this R and the feedback capacitor CF. So by changing the value of this R and CF, we can change the slope of this output signal. Similarly, if we apply the sinusoidal signal at the input, that is sine omega t, then at the output you will get a cosine signal, that is cos omega t. And likewise, if you apply the square wave at the input, then at the output you will get a triangular wave. Now here the amplitude of the output signal depends upon the value of R and CF, and that will be get clear to you when we will take few examples based on this integrator circuit. So now so far we have seen this simple integrator circuit, and we understood that using this circuit we can integrate any input signal. But in the real life, if you use this integrator, then you may not get the desired output which you should get using the theoretical calculations. So let us understand the limitations of this simple integrator circuit, and let us also see how we can overcome these limitations. So to understand that, let us write the output voltage in terms of the impedance of this capacitor and the resistor. So now we know that the reactance of this capacitor can be given by the expression 1 divided by omega c, right, which is equal to 1 divided by 2 pi times Fc. So we can write the output voltage V out as minus Xc divided by R times the input voltage V in, or we can say that the gain of this op-amp will be equal to minus Xc divided by R, that is equal to 1 divided by 2 pi times Rc into F. So from this expression you can see that at 0 Hz or at very low frequencies, the gain of the op-amp will be very high, and ideally it will be equal to infinite. But practically the gain of the op-amp will be limited by the open loop gain of the op-amp. So at 0 Hz, the gain of the op-amp will be equal to the open loop gain of the op-amp, because at 0 Hz or at DC level, this capacitor will act as a open circuit, and because of that the input voltage will be get amplified by the open loop gain of the op-amp. So output will always be get saturated, and as the frequency increases, the reactance of this capacitor will reduce, and because of that the output voltage will also reduce. So if you see the frequency response of this simple integrator, then it will look like this. So at 0 Hz or at DC level, the gain of this integrator will be equal to the open loop gain of this op-amp, and this open loop gain used to be in the range of 10 to the power 5 to 10 to the power 6. So in decibel we can say that it is equal to 100 dB, and as the frequency increases, the gain will reduce. Now suppose if you are using this op-amp at, let's say, this frequency, then you should not face the problem of very high gain of this integrator. But even if you use the op-amp at this frequency, then also it is quite possible that your output will be get either distorted or saturated. Now the reason for this saturation or distortion is the input offset voltage of the op-amp, because in the real life scenario the op-amps which we are using are not ideal op-amps, and every practical op-amp has some sort of input offset voltage. So even though this input offset voltage is of few millivolts, but still it can saturate the output of this op-amp. So let's say few millivolts of input offset voltage is present at this terminal. So this input offset voltage will be get integrated by this capacitor, and eventually the output of this op-amp will go towards the saturation. So in this way, even though you are operating at higher frequency, but because of this input offset voltage, it is quite possible that your output will be get saturated. So we can avoid this problem by introducing a one more resistor in the feedback in parallel with this capacitor. So in this way, by introducing a one more resistor in parallel with this capacitor, we can avoid the problem of saturation of the output voltage. Because now if you see at low frequencies, this capacitor will act as an open circuit. So at DC voltage or at low frequencies, the gain which is being seen by this op-amp will be equal to minus RF divided by R1. So even though few millivolts of input offset voltage is present at the input terminal, it will only get multiplied by this factor. So in this way we can avoid the problem of saturation. So if you see any practical integrator, you will find this feedback resistor in parallel with this capacitor. So moreover that, if you see any practical integrator, you will also find a resistor which is being connected at the non-inverting terminal. So basically this resistor is connected to avoid the effect of input bias currents. So we will see more about this input offset voltage and the input bias currents in a separate video. So now because of this feedback resistor RF, if you see the frequency response of any practical integrator, then it will look like this. So as you can see here, at low frequencies, the gain which is being seen by the op-amp will be equal to constant, and that is equal to RF divided by R1. And as we go beyond certain frequencies, then you will see the reduction in the output. And if you see the response of this integrator, it is very similar to the response of a low pass filter, and in fact it will act as a low pass filter. So let us say here the 3 dB frequency or the cutoff frequency of this integrator is FL. So now if you apply any input signal which is having a frequency lesser than this cutoff frequency FL, then the op-amp will act as a inverting op-amp, and it will provide the constant gain of minus RF divided by R1. So to use this op-amp as an integrator, the input signal should have a frequency larger than this cutoff frequency FL, and this cutoff frequency FL can be given by the expression 1 divided by 2 pi times this feedback resistor RF into CF. So as you go beyond this cutoff frequency FL, you will see the reduction in the output voltage, and at one particular frequency the gain of this integrator will be equal to 0 dB. So let us say this frequency is a 0 dB frequency, or let's say F0. So this F0 can be represented as 1 divided by 2 pi times R into CF. So for the proper integration of input signal, the input frequency should be larger than this cutoff frequency FL, and for the proper integration, this signal frequency Fs should be at least 10 times this cutoff frequency FL. So to integrate any input signal properly, the input signal frequency should be in between this cutoff frequency FL and 0 dB frequency F0. Well, practically you can also go beyond this 0 dB frequency, but if you go below this 0 dB frequency, then you will see the attenuation in the output signal. So for the proper integration of any input signal, it should lie between this cutoff frequency FL and F0. So now let us take some example based on this integrator so that the concept will be get clear to you. So here we have a practical integrator circuit, and in this circuit we have been asked to find the low frequency limit for this integration. So here the value of this feedback capacitor is 10 nanofarad and the value of this feedback resistor is 100k, while the value of this resistor R is 1 kilo ohm. So we know that the expression of this cutoff frequency FL is equal to 1 divided by 2 pi times RF into CF. So if we put the value of this RF and CF, then the value of this cutoff frequency FL will come out as 159 Hertz. So for the proper integration of input signal, your input signal frequency should be larger than this cutoff frequency FL, and for proper integration it should be at least 10 times this cutoff frequency FL. So in this way, based on your input signal range, you can design your integrator. So now let us see the second example. So in this example, the circuit is the same circuit which we have seen in the last example, but here the input signal now is a sinusoidal signal. And if you see here, the frequency of the input signal is 5 kilohertz. Now we have already seen that the cutoff frequency of this integrator is 159 Hertz. And for proper integration, the signal frequency should be at least 10 times this cutoff frequency, which comes out as 1.59 kilohertz. Now here if you see the input frequency, it is 5 kilohertz. So this signal will be properly get integrated. So let us find the expression for the output voltage. So we know that the output voltage V out can be given by the expression minus 1 divided by RCF multiplied by the integration V in dt. Now here the value of R is 1 kilo ohm and the value of CF is 10 nanofarad. So let us put all the values into this expression. So now if you put all these values and integrate this signal, then you will get 10 to the power 5 divided by 2 pi times this 5000 multiplied by cos into 2 pi times 5000 t. So if you simplify it, then you will get 3.18 times cos of 2 pi into 5000 t. So this will be the output voltage V out after the integration. So as you can see here, the amplitude of the output voltage depends upon the value of R, CF and the input signal frequency. So now let us see one more example based on this integrator circuit. So in this example, the circuit is same, but now the input signal has been changed from the sinusoidal signal to the square wave, and we need to find the output voltage at this end. Now we know that whenever we apply any square wave to the integrator, the output voltage will be equal to triangular wave. But let us find the amplitude of this triangular wave, and let us also see whether this signal fulfills the criteria of our integration. So if you see here, the time period of this square wave is equal to 100 microsecond. So in frequency, if you say, the frequency is equal to 10 kilohertz. Now for this circuit, we have already seen that the cutoff frequency FL is 159 Hertz, and here the signal frequency is way beyond this cutoff frequency. So it is ensured that the input signal will be properly get integrated. So now let us find the amplitude of this integrated signal. So to find the output voltage, let us divide this square wave into the different segments. So we can say that for 0 to 50 microsecond, our input signal is 2 volt, while from 50 to 100 microsecond, our input signal is minus 2 volt. So we can integrate individual segments and later on we can add the individual responses. So for the first segment, our output voltage VO1 will be equal to minus 1 divided by R times CF integration V1t dt, which will be equal to minus 10 to the power 5 integration 0 to 50 microsecond 2 into dt. So that will be equal to minus 10 to the power 5 into 50 microsecond into 2. So if you simplify it, then you will get the output voltage as minus 10 volt. So we can say that for 0 to 50 microsecond, the voltage swing is minus 10 volt, or we can say that the output signal is going from 5 volt to the minus 5 volt. Similarly, if we integrate this particular segment, then we will get the same 10 volt voltage swing but in a opposite direction. So in this way, if you see the output will vary from 5 volt to the minus 5 volt. And as the input signal frequency is far beyond the cutoff frequency, you will see the proper integration of the input signal. So before I end up this video, here is and to this circuit we have applied this input signal. So you need to find the integrated output signal. So let me just give you the hint about the shape of the output waveform. So as you can see here, we are applying the input for a 1 millisecond. So for this particular 1 millisecond, you will see the output will look like this. And from 1 millisecond to 4 millisecond, as there is a no input, so the output will remain as it is. And once again, from 4 millisecond to 5 millisecond, as we are applying the input, you will see the output will look like this. So if you see the output waveform will look like this. But just calculate the value of this output voltage and do let me know that value in the comment section below.